question of the day. Hi, I'm Professor Q. So glad to be with you. Yes, I was just making sure I was looking beautiful for you because today we're going to be talking about mirrors. And what are the physical properties of mirrors? Well, that's a good question. Well, one main physical property is that it reflects. That's right. When you look inside the mirror, what do you see? You see you. How beautiful you can be. So, with reflection today, there are many different types of things that we can discuss about reflection and what people see and how there are different types of reflections. So I have a question for you right now. Scenario. What do you see if you were to walk into a room that was completely pitch dark? Go ahead and think for a moment. Could you see an apple on a table? Let's think about that for a moment. So what did you think about that response? Would you be able to see a red apple in a pitch black dark room? Well, what about a green apple, perchance to say? Would you be able to see it at all today? Well, some of you may say yes, and some of you may say no. Question is, how many of you have ever gotten up in the middle of the night just to be able to get a drink of water? And you were able to kind of stumble your way through to the kitchen. Because is it that you knew the outline of where all the furniture was? Or was it because maybe you saw that your eyes became adjusted to light? Or was it that you saw maybe a small little light piercing through the darkness to guide you to your way? That all may be good and true, but to be able to see the red apple in pitch black dark is really not true, because you may be able to feel the object, but our eyes cannot perceive it because there is no light in a pitch black dark room. So, question also is trivia time. How fast does light travel? Think about it. Write that down in your interactive science notebook at this point. Zoom! Wow! So what did you think? Light can travel 186,282 miles per second. Wow! Isn't that amazing? But what does that mean to you? That's pretty fast, right? Well, think about this. If you were a light ray, that light ray would be able to travel 7 times and a half around in 1 second. That's how fast light travels. Whoa! So, how does light help us? And where does light rays come from? Well, light rays can be actually from natural and man-made. Where would we find natural light? That's right! Solar energy! The sun! The sunlight rays are able to come and provide us not only light, but also heat energy too. Now, what about man-made? Well, of course, we have our handy-dandy flashlight. That is definitely man-made. Or have you ever seen those neon open signs in storefronts? Blink on, blink off. That's right. Those also help to have some type of light as well. Light is all over, but the question is, how is light viewed by us? Well, reflection is the key. And the law of reflection is one of two instances that we'll be discussing today. So, are you ready? So am I. Fantastic. Well, before we actually figure out a little bit more about reflection, the question is, well, we know that how fast light travels, but the question is, how does light travel? In what way? So for our understanding, let's do a quick experiment, shall we? Okay, at this time, we're going to see that we have a setup. We have 3 index cards and we have a solid backing. I would like for you to please go ahead and illustrate what this diagram looks like in your science notebook. Let's go ahead and pause the video. Okay, excellent illustrations, class. So, what I have asked you is to find out, well, number 1, to draw the diagram. Secondly, the question is, how does light travel? We know how fast it does, but how does it travel? And before we really get started with these experiments, one safety tip that I must tell you about light. Question, should we shine a flashlight or a laser light in anyone's eyes? No, because why? Well, we don't want to ruin anyone's eyes at all, so we must always be careful of where we are pointing our flashlight and our laser. Okay, now for the safety tip, let's get into the exploration, shall we? So I am going to attempt with my handy dandy laser here to be able to shine light through the holes located in the index card. And what do you think will happen? All right, are you ready? Here we go. What do you see? Do you see the light? There it is. Now the question is, if I move my laser light to the left just a tad, will we be able to see the light on the backing? Make your prediction now, please. All right, here we go. Let's try it. No, I can only see that the laser light is on the first index card. So let's move it a little bit back to see. There it is, right in the middle again. So what is your prediction then if we were to move the laser light a tad to the right? Go ahead and make your prediction. All right, are you ready? Here we go. No, once again, the light is only seen on the first index card. Wasn't that a great experiment? So we know how fast light travels. How fast does it travel? You're right, 186,282 miles per second. I can't even say that fast enough, can you? And also, we identified that light travels in a straight line. So that experiment helped to be able to give evidence of such as that. So let's go forth now and do another experiment to see a little bit more about the reflection properties of a mirror. Fantastic! Are you ready to explore? So am I! Oh, this is so exciting! So, I see an object over in this area. What could it be? It's a little bear! Oh, I love little bears! So, we have a mirror and we have a bear. How many bears do you see in the mirror? Raise your hand. 1 finger, 2 finger, 3 finger, 4 finger, 5 fingers. 1 finger for 1 bear. You're right. But my question is this. How many bears do you think you would see if I added another mirror? Ooh, put on your thinking caps and let's find out soon. Okay, so how many bears did you see? You saw 1, that's right. And the question is, well, now that I have 2 mirrors angled in this direction, like an arrow, but the opposite direction, how many bears in the mirrors do you see? Once again, how many bears in the mirrors do you see? Go ahead and write that down in your science notebook, please. You're right. You should see 1, 2, 3 bears in the mirror. But wait, someone said, but I see 4. How can that be? True, you do see 4, but that 4th one is actually the included one that I can take and hold, because the other 3 are in the mirror to be. Excellent job. All right, this is so much fun. I love just exploring science with you today. So we see that there's 1 bear here, but can you see any in the mirrors as they are angled away from the bear? No, you sure can't. So you never know what you would be able to see. Now, if I were to angle this mirror this direction, can you see anything in the mirror? What do you see? Oh, it's our guest. This is hi, Buttons. Buttons, can you say hi? Hi, Buttons. Look at those reflective eyes. So, this is so exciting. So what can you conclude then from mirrors? You're right. Mirrors reflect, and they reflect on the images by which are viewed in their immediate location. And it's important how that image is reflected. So, are you ready to explore one more time? So am I. Oh, hi there. You just caught me exploring a little bit more with light. So what am I actually doing at this point? Well, I'm trying to see how does light reflect off of a mirror? Or in other words, it seems like it's bouncing off. You're right. You heard me say bounce. So let's take a look. I have my laser and I am going to point my laser towards the direction of one of these arrows, sticks, and to see how it would actually bounce off. And does it? Well, let's see. Oh, there it is. Absolutely. Wow. So this is kind of showing me that there is some type of symmetrical angles that may be going on. So I'm going to place this, and here it is. That's right. Well, that's amazing. Well, this visual kind of helps with one of the laws, parts of the law it is, of the law of reflection. Well, what does that mean? Well, let's take a look over here at this diagram, shall we? So we have a smooth mirror, and we have light rays. The light ray is going to be coming from the light, and as it will start to hit this point, it's actually going to be called the angle of incidence. Not accident, but the angle of incidence. And this is actually the point of incident where it initially hits that mirror. As soon as it hits that mirror, it immediately bounces off. Just like if I were to take a tennis ball and bounce it off of a mirror, hit the mirror, and it bounces right back. Well, here you go. That light ray will bounce off, and that is called the angle of reflection. Now, there's something very special about the angle of incidence and the angle of reflection. Take a look at these two angles. What do they have in common? You're right! They are symmetrical. Well, what does symmetry mean? Symmetry means they're equal, they're congruent. So therefore, the angles are the same. So reflection is symmetrical. I say reflection, you say symmetrical. Reflection. Reflection. Fantastic. So now this middle line is actually called the normal, and it shows the division of the angle of incidence to the angle of reflection. So that is actually one part of the law of reflection. It's amazing to hear and to see how reflection can be. And remember, reflection can be regular. This is regular reflection where it bounces off of a smooth object. But what about other objects? Are other objects smooth? Of course not. Take a look. I have my handy dandy bubble machine maker here, and you see the curvatures? Well, is light reflecting off of this bottle? Yes, it is. But it's reflecting in different angles. For each point of ray that hits the bottle, it has a different angle of incidence and angle of reflection. So that's why we're able to see all these different types of lights. Now, another thought I'd like for us to see and experiment with is, oh, this is so much fun. Have you ever had the opportunity to play and explore with these? Well, what is this? And what is this? Well, these are prisms. Absolutely. Have you ever looked at prisms in the light? And what would they produce? Wow. Well, let's do that now. Are you ready? Here we go. Oh, that's pretty bright. Oh, how pretty. What do you see? What shape is that? Might be. You're right. It's triangles. How neat. But what I'd like for you to also take a look is the circle around the perimeter, the circumference. Do you see different colors? Oh my goodness, I think I do. Take a look right here. Can you see some blue? Maybe a little bit of white, a little bit of yellow, and a little bit of red? What might that be? What type of coloration? Did you say the rainbow? I think you're right. What colors are in the rainbow? Have you ever heard of the saying, Roy G. Biv? R is for red, O is for orange, Y is, what do you think? Yellow, you're right. What about the G? Green. The B? Blue. Let's see, what am I missing? The I. Oh, some of you may not know that. It's indigo. And what about the V? It's violet. Those are the colors of the rainbow. How did we find them? Through reflection. Absolutely. And also refraction. But we'll get to that at another time. But the most important thing is to look at the types of images that one can see and how that reflection is of the light. Okay, wasn't that fun, boys and girls? So, oh, we're not done quite yet. My question is this: does light absorb itself into different colors at different intensities? Meaning, if I have yellow and I have black, which color do you think the reflection would be absorbed into most? The yellow or the black? Go ahead at this time and write that down in your journal. Well, hello! We have another special guest. Say hi, Twinkles. Twinkles is going to help us determine which color do you think would absorb the intensity of the reflective light ray. You think the black one is? Or is it going to be the yellow? Let's find out. Take a look. Oh, what's over here? That's right. Well, see how intense that is? And then what happens when we move it over here? Which one gets brighter, Twinkles? Twinkle, twinkle, little star, which do you think it are? Wow. Okay. The yellow is brighter and lighter, and the black is absorbing. Well, that kind of makes sense. How many of you have black cars? And when you get in the summer into that car, is it really hot or is it really cold? More than likely it's really hot because black absorbs the heat energy and the light rays. Whereas in the summertime frame, you would want to wear a little bit more lighter, brighter colors because what does it do? They reflect. It bounces off the light. So that way you feel a little bit cooler in the summertime frame. Well, I think we have our special guest Twinkles here. She's just gonna chill out as summer comes along too. Hi guys. So Twinkles still is gonna be here helping us out, talking a little bit more about reflection. In fact, she was discussing the importance of how cats can actually see. Well, cats have a shiny layer, otherwise known as tapetum lucidum, in the back of their retina. So that way when lights actually hit their eyes, it reflects that light and it looks like it's a glowing type of eyes staring at you. But that's their special trait that they have. So before we leave, I also want to just briefly discuss how light travels. We discussed about regular and irregular, but what about different types of colorations? Now we discussed the intensity of light and how it's absorbed, but what about light going through clear objects or opaque objects or otherwise known as translucent objects? Whoa, well that's a lot of vocabulary. Well, what do you mean, Dr. Q? Well, what I mean here is as this heart, the sand time of life, well, this clear glass is called transparent because you can see through it. Whereas my bubble machine here at this point, well, even though it has some bubble juice in it, it's still somewhat translucent. I can see through it somewhat, but not as clear as that as the transparent. And last but not least, well, my other bubble machine, this one, actually you can't see it at all. So that's called opaque. So is another opaque object on the table? You're right. Well, we have the flashlight and we have the apples and so much more. So thank you so much for joining in to us today and tuning in and having a little bit more conversations about reflection. And I want to leave you with a little reflection dance because it's always fun to have a party in science. So I want you to raise your right hand, which will be the angle of incidence. And let's pretend that we are going to be having our light ray go on the table and we're going to take our elbow and connect, which our left hand will be the angle of reflection, and then we're going to move up. So we have the angle of incidence and angle of reflection. We have the angle of incidence and angle of reflection. Come on, let's say it one more time. The angle of incidence, the angle of reflection. So you can start moving on like this. So Twinkles and I are going to go party on in science reflection light. And remember, be strong, be great, and good, better, best. Never let it rest till the good gets better and the better gets best. Go. Hey, what do you say? What's the question of the day? Hi there, I'm Professor